this target, these 7 pebbles cannot reach it. So that's an unsolvable configuration. And so the pebbling number is bigger than 7. In eccentricity at a vertex, that's just the farthest distance from that vertex in the graph is the eccentricity. The pebbling number has to be at least 2 to that distance, 2 to that eccentricity, for this simple reason that you keep having half and half and half and half. You'll need to start with at least that. So that's a primitive upper bound. In general, it's for the pebbling number of the graph, we would maximize the local pebbling numbers over all targets R. And so similar to this, the worst case, the biggest number is going to be 2 to the diameter. But you could also have somebody, if you had, say, 15 vertices and you only bought 14 pebbles, somebody could place 1 pebble at every vertex except the target, and then you wouldn't be able to move at all. So that would also be an unsolvable configuration. And so I need to buy at least as many pebbles as the number of vertices. A simple pigeonhole argument gives an upper bound of n times 2 to the diameter. So this pebbling number, this parameter is well defined, but that's a pretty large gap between these 2 lower bounds and this big upper bound. Okay. Let me give you some of the tools that we use in the theory. One is called the R potential. And it has this formula, and let's just make sense of it. It's counting how many pebbles are at the target R. But for the vertices that are not at R, it's taking half of them and taking the floor. So for example, half of 7 is 3.5, the floor is 3. So that describes how many pairs of pebbles are at that vertex. It's 3 pairs. Well, that tells you how many moves you could make from that vertex. So this is describing how many moves are possible to start, plus how many pebbles are actually already there. And so if you start with a pebbling step from U to V, the first potential lemma says that the potential can only decrease, that you lose potential. It could stay the same if the number of pebbles at the arriving vertex is odd. It could stay the same, otherwise it decreases. So this is a nice measure to keep track of when you're losing potential, when you're losing the ability to move. And because this formula has the count that we described, it's really counting the maximum number of pebbles that could reach R. So this really immediately gives you some lower bounds on pebbling numbers and knowing when a configuration is unsolvable. The third potential lemma gives you a lower bound on how big the potential is, which is very useful. You look at the size of the configuration, you subtract the number of vertices, and you add this, what we call the support. So the support of C measures how many vertices have pebbles on them. We call these positive vertices. So it counts the positive vertices. Like any function, this is what the support of a function is. So you add that up, you take half of it, and you take the ceiling, and without describing, it's a simple proof that you could write yourselves as a lower bound on the potential. So these are 3 key lemmas, the potential lemmas. And that's one of the techniques that we start with. Another technique that's somewhat similar is a measure we call the weight, or the R weight. So if the target is R, we can describe the R weight at some vertex V by looking at the distance between V and the target R. And so it's the weight is half, 2 to the minus that, so half to that distance. So the farther away you are from the target, the less weight that vertex has. And you have to compensate by having many pebbles out there to be able to move them towards R. So it helps describe how you lose pebbles when you're trying to reach the target. And so we have weight lemmas as well. We have 3 introductory weight lemmas that describe similar things. That when you move, take a pebbling step from U to V, again, your weight can only decrease. It could stay the same if you're moving strictly toward the target. So when the distance, this, by the way, I've accidentally written this in the wrong direction. When the distance decreases, when you get closer to R and your pebbling step, that's called a greedy pebbling step. And these are critical types of pebbling steps to keep track of because it does preserve the weight. This also gives an upper bound on how many pebbles can reach R, because you can then add up all the weights of the vertices over the vertices in the configuration. And what I've also accidentally done is forgotten to write C of V times that. So let me sneak that in there. How's that? We fixed it. Okay, so that's the weight of the whole configuration. And there's only one time when this weight is a characterization of solvable configurations, and it's on a path. But that's a very useful thing to happen. As it turns out, if the target on a path is the leaf, then the configuration is solvable if and only if the configuration has weight at least 1. It's a lovely little induction proof you could write down in a few minutes. And so that's handy as well. Okay, so with these tools, I'll give you a sense really quickly of some of the things that you could write an induction proof of the pebbling number of a path. It's 2 to the diameter of the path. The same is true for a cycle. This C sub 2K is a cycle on 2K vertices. Cycle being like this black graph here. The number is a little bit different for an odd cycle. It's about 4/3 times that formula. And this is an example of a 7 cycle. And I'll sketch the argument of this formula for this example instead of in general. And let me first give you the lower bound. Here, K is 3. 2K plus 1 is 7. And you see we've got a 7 cycle. This is symmetric, so I can choose any target R. They're all the same. So what is this formula? Well, you plug it in and you get 11. By the way, this is the notation here. It looks like it's part floor, part ceiling. This is the nearest integer. So for example, 2 to the 5th is 32, divided by 3 is 10 2/3. That's closer to 11 than it is to 10, right? So that's the formula that we use. And that's why I won't bother the technical actual proof, because it's not as pretty. You'll see it by this example. So if we want a lower bound, we take a configuration of size 1 less than that, 10 pebbles, and here's one in green. So that configuration is size 10. If this is solvable, then it's either solvable along the path to the left, or it's solvable along the path to the right. So let's look at the blue one that I've drawn. It's a path on 5 vertices, and what we just learned was that this configuration is solvable if and only if the characterization of weight being at least 1 holds. However, this weight, these 5 pebbles are distance 3 away from the target, so that's 1/2 cubed times the number of pebbles. The other on that path is distance 4, so that's 5/16. This adds up to a little bit less than 1. So it's unsolvable on that blue path. By symmetry, it's unsolvable the other way as well. So this is an R unsolvable configuration. And so we know that 11 is a lower bound, and we'd like to say that it's also an upper bound. So let's try that. So for this, let's suppose that we have a configuration in green, and we'll put A pebbles here, B pebbles there, C pebbles there, and so on. Okay? On the blue path P, if the configuration is unsolvable, we use the characterization that we just had that says on the left is the weight, and you can see that the exponents in the denominator increasing as you get farther away on that path, is less than 1 because it's unsolvable. Let's clear the denominator. So that means multiply by 16 everywhere. So now we just have integer coefficients, and that's a little bit easier to see. But it's also helpful once you've written it that way to know that if it's less than 16, it's at most 15, because these are integers that you're adding up. So we write it that way. There it is. Now you make the same argument symmetrically with the path on the right. It's mirror image P prime. And you get the symmetric equation, or inequality, I should say. And once you have these two inequalities, you simply add them together to derive this one. This is a typical thing that you do when you're teaching linear optimization, right? You get them to realize, the students can see that if you have some inequalities, you can add them in various multiples together and derive new ones. Well, now what we do is the smallest coefficient here is 3. So let's divide by 3. And that's what you get. There's a 10 on the right. And now you notice that the configuration size is A plus B plus C plus D and so on. And if I increase the coefficients, I get something bigger. So the size of C is at most 10. We started with saying if C is unsolvable, and now we've said, therefore, its size is at most 10. By contrapositive, if you have 11 vertices, then it must be R solvable, and that's the upper bound. So it's a little bit sneaky when you see it the first time, but it's a powerful tool, and it gives a quick result. Okay, so let me run through just a couple of other results. K sub n, this is the complete graph on n vertices. You n vertices, and complete means you join every pair of vertices. And by pigeonhole principle, you could prove that in a matter of minutes. or less. The very first paper in this theory was written in 1989 by Fan Chung, and she proved for this graph, Q to the D, this is called the D-dimensional cube. The three-dimensional cube is what you think it is. It looks like this three-dimensional cube, where the name comes from, right? And so you can do that in higher dimensions and ask what is the Pebbling number. And it turns out to be 2 to the D. That's the number of vertices of the cube. And so that turned out to be very nice. Another nice thing that I'll show you a little bit later in the talk is the Peterson graph, which many of you might know. Very famous graph for many reasons. Has Pebbling number 10, which is also the number of vertices. Now, these types of graphs are of most interest to the field. These are called class 0 graphs, when the Pebbling number of a graph is equal to the number of vertices. Very much interested in this family of graphs. And these are two examples, the cube and the Peterson graph, and the complete graph, all three of these. Another early result from about 30 years ago is that if a graph has diameter 2, then the Pebbling number is either the number of vertices or 1 bigger. And this is where the language of class 0 comes from. It's number of vertices plus the class. Number of vertices plus 0, that's class 0. Number of vertices plus 1, that's class 1. And a few years later, a graduate student and another colleague of mine, Clark and Hopeberg, we were able to characterize how to determine which graph was which. And the central characteristic of the class 1 family is having this graph called the pyramid. I won't go into that. Has other requirements, but that's really the central structural difference between the two classes. As a corollary of that characterization, we were able to prove that if a diameter 2 graph has connectivity at least 3, then it's class 0. And we conjectured this type of phenomenon holds in general. And we didn't prove this for another 5 years or so. A whole group of us was able to prove if the diameter is D and the connectivity was exponential in D, this is 8 times 4 to the D, then you get a class 0 graph. Any kind of theorem on the connectivity to say how big it has to be at least 2 to the D divided by D. So there's a big gap there. The upper bound is about the square of the lower bound. And so if you want a nice problem to work on, that's a really good one. People are very interested in closing the gap between those upper and lower bounds. Okay, let me share some of the biggest conjectures in the field before I get to talking about one of them in particular. Graham's conjecture is certainly the most famous and the oldest. This is a conjecture about the Cartesian product of graphs, which is denoted by this square here. Cartesian product of graphs is a little bit like if you took the Cartesian product of paths, you get the grid paper that we all write notes on. I won't go into the more details about the actual definition, but it's a very lovely product formula that's conjectured. If you know the Pebbling numbers of G and H, then you multiply them together to get an upper bound on the Pebbling number of the Cartesian product. That's a conjecture. It's still open. There's been a lot of work on it, but it's still wide open. And so there's plenty of room to jump in and contribute to that area. Now, my esteemed colleague who introduced me generalized this, and this is also very open. This is a wonderful generalization. I haven't described this notation, but if you use just pi, that means there's one vertex with one request, and you have to satisfy all of them individually like that. Here, it's one vertex, but it's requesting t pebbles. That's the difference. That's the generalization. And then this would be the formula that is conjectured. And there's been some progress there as well, not as much. Some years after his conjecture, another student and another colleague, Herskovich and Hester, we conjectured this, that if you have, going back to the original definition I started with, a pebbling target number for G and a different target for H, again, you take the products of those, and it's an upper bound on targets of this type. Okay, again, without getting into too much detail, those are very good conjectures to look at examples of. Another well-known is, again, given by Herskovich, Hester, and myself, and it's called the weak target conjecture. So it's trying to figure out a bound on the general target pebbling number, and it's saying it's got an upper bound of the target pebbling number where all the targets are coming from the same vertex. The idea is that if you know which vertex requires the most pebbles to get there, then that should be the vertex that's requesting all of them instead of spreading the requests around the graph. That's the idea behind this conjecture. And it's been shown true for a number of cases, but less work has been done there. So another place for people to get started on some work of great interest. Liliana Alcón, one of my colleagues in Argentina, she and I were able to sharpen this conjecture to prove some results. It takes the weak conjecture and it says a tighter upper bound is given by knowing the support of the target. So you can subtract off the target and add one. And that's the strong target conjecture. If you know a lot about chordal graphs, I won't describe them. But as I mentioned, discovering if a configuration solves a target is NP complete. So a lot of people want to know families of graphs that do have polynomial solutions. And we believe that chordal graphs that don't have that pyramid, that triangular looking graph I showed you before, if they don't have that pyramid as an induced subgraph, we believe that then you can calculate the pebbling number in polynomial time. And so if you're a computer scientist out there that likes doing complexity of algorithms, this is the problem for you. That's the chordal conjecture. And there's been a lot of good progress in that direction. Okay, finally, this is the newest conjecture, and a graduate student that I currently have named Paul Fay, he and I have been working on graphs that are vertex transitive. That means, like the cycle, every vertex looks the same. Technically, if you look at the automorphism group of the graph, right, functions on the vertices that preserve edges, then picking any two vertices, there's an automorphism that takes one to the other. If the graph has that property, it's called vertex transitive. So very, very highly symmetric graphs. And we believe that most of these are class 0. So to say what most means, we look at graphs we call wide. And this is where the number of vertices is bigger than 2 to the diameter. You can remember early on, these are the two lower bounds, the two elementary lower bounds for the Pebbling number. And so if you're dealing with a graph where this is the better lower bound, we call that a wide graph. It's very wide if not even requiring the number of vertices, just the minimum degree of a vertex, right? So look at all the vertices, see which vertex has the fewest edges. That's the minimum degree. If that is bigger than 2 to the diameter, that's very, very wide graph. We call it very wide. So our conjectures, the weak one is that very wide vertex transitive graphs are class 0, and the strong one, strong vertex transitive conjecture, is that just wide ones are. That's a bigger group of graphs. And we've been building some evidence toward this. So I want to show you that evidence and also show you a technique which generalizes what I showed you earlier. And this is to look at weight functions, not just the weights that I showed you, but now we call them weight functions, where the function on the vertices is to all the non-negative reals. What you do is you take a pair where T is a rooted subtree of G, and it's rooted at the target R. So it doesn't have to be a spanning tree, just any subtree. And the weight function has to behave nicely on that tree. That is to say, when you, let's say you hang the tree, redraw it, take the root and hang the tree down. We like to say it. The neighbors and the neighbors and the neighbors go down and down and down. So the downward neighbors moving away from the root are called children of the vertex. And so the behavior is this. If you take any vertex that's in the tree, but it's not the target, look at its weight. It has to be at least double the weight of any of its children. That's the only constraint. It could be much more than double, it could be triple, it could be 10 times more, whatever, but it has to be at least double. Off of the tree, as well as the target R, the weight has to be 0. And that's the restriction on the weight function and the tree to call it an R strategy. All right, so what do we do with this? This was something that many years ago, about 15 years ago now, on my first trip to Jaipur, actually, I was taking a trip through the streets, and this idea came to me as I was looking over at an elephant next to me in the street. I thought, wow, this doesn't happen in Virginia. And this idea came to me, and you know, elephants have a lot of weight. So this was the weight function lemma. What it says is that if you take a configuration C that is R unsolvable in G, and you have a strategy, an R strategy, TW, then the sum of the product of weights and the configuration, this is really just an inner product of vectors, you can think of it as, has an upper bound of the sum of the weights. Okay, so that's what the weight function lemma is. It's reminiscent of the way we used weight on the cycle. And I'll show you how. On a more complicated graph, this is the Peterson graph that many of you are familiar with. It's one of the most fundamental graphs to be familiar with in graph theory. It's important in graph coloring and topological graph theory and algebraic graph theory, a lot of different things, homological graph theory, many, many things. And so it's of great interest here. So what do? I've outlined here, and I'll make it a little bit bigger. You can see that I've highlighted in orange some of the edges, and it has a structure of this tree that we've hung down from R. So we're starting with an unsolvable configuration, C, and C puts A pebbles here, B pebbles there, C pebbles there, D pebbles here, and so on. Now the orange weight function, you can see that has weight 4. Its children have weight 2, so that's exactly half. And again, exactly half of that is 1. And what the weight function lemma says, it gives you this inequality. Okay, 4 times A plus 2 times D plus 2 times E plus 1 times F, and so on. And if you add up the 4 plus 2 plus 2 plus 1, 1, 1, and 1, you get 12. So that's what the weight function tells you. Well, let's do it with another tree. Here's a blue one. Same kind of thing. It's not a spanning tree. It doesn't reach A or C, but it is a rooted tree rooted at R. And it also gives a very similar inequality. Then we can do it with this red tree and get yet another inequality. So what do we do with that? We can add them together just like we did before. And you'll notice that every coefficient adds up to 4 exactly. Well, as before, this is exactly 4 times the size of C. So we've started with the hypothesis that C was R unsolvable, and we derived that 4 times the size of C is at most 36, which is the sum of the 12s. Divide by 4 and you get C is at most 9. That means the pebbling number is at most 10. Right? And this has 10 vertices, and we already knew that 10 was a lower bound. So the pebbling number equals 10. This is a class 0 graph. Peterson graph is very symmetric. It's vertex transitive. And there's a whole class of graphs just like it. We can give a better overview of what that sort of putting strategies together looks like if we redraw the Peterson graph like this, where we draw the neighbors first, and the neighbors of those neighbors, that's the second neighborhood. We can take a blue strategy and use 12, 6, and 3 instead of 4, 2, and 1 that we had before. Works still just fine. And instead of being so careful that we could look at all symmetries that fix R. Every symmetry of the Peterson graph that fixes R. We look at all the images of those strategies, of that strategy. We now have many strategies. And we take the average weight function over all of it. Well, there's a total weight of 12 here amongst 3 vertices. So that average is 12/3, which is 4. Here, the total weight, 6, 6, and 4 3s is 24. And there's 6 vertices. The average there is also 4. So it's a little bit easier in that realm of just looking at all the automorphisms, and this vertex transitive graph gives you a quicker proof of this class 0 graph. So we can generalize these graphs and look at things that are called generalized Johnson graphs that have this definition. The vertices are all the subsets of M elements of size K. And the edges are those pairs of sets that have intersection size exactly I. And these are all vertex transitive because the definition is completely symmetric. The Peterson graph is this example, 5, 2, 0. A broad class of famous graphs are called Nesser graphs, and they have these parameters. And there are others of interest that fall under this category as well. There are Grassmannian graphs and a whole bunch of other families, things like this. They come up in differential geometry and a whole bunch of other subjects. So this family is a huge playground to look at, investigate this conjecture with broad interest in many subjects. We already know that the diameter 2 graphs are class 0 because of the connectivity result. And so far, what Paul Fay and I, my student, have dug out are diameter 3 graphs are class 0 for these parameters. Over the last several years, many students and I have whittled down this particular example, and we don't know if it's class 0 yet. It's either class 0 or class 1. We've been working on that for years. If you can find that one, then more power to you. Okay, so let me finish with, there are many, many variations on pebbling where you have the same solvability definition, but you change the question. You might be interested in another aspect of pebbling. Instead of what's the largest unsolvable configuration, you might be interested in what's the smallest solvable one. And that's optimal pebble. Or you can ask, what if somebody just threw the pebbles onto the graph at random, which happens in many applications. And so that's a good randomization if your favorite thing to do is ask probabilistic questions. That's called threshold pebbling. There's fractional pebbling, bounded, stacking, cover pebbling, lots of variations, and many things to work out there, and some applications even into combinatorial number theory and combinatorial group theory. So there's lots of work to jump in and see what there is to do. And there are plenty of resources to look at. There's an article that a colleague and I wrote for the Notices of the American Math Society 5 years ago that gives a broad overview of some of these. On the web, if you type in graph pebbling pages with my name, that'll come up. That's a bit of an older set of pages. My newer site has publications on there that are good to look at and find references and new results. And then I have a forthcoming book that I'm trying to finish this year. So by this time next year, we hope that it'll be ready, that you can access. And then that's all I have for you. So I really, really thank you for your attention, and I welcome any questions. And once again, I especially thank Professor Lordasamy for inviting me. I will be in Madurai, is it Madurai? No, Bengaluru this summer in June. And so many of you I hope to see there. Thank you again. Go back to my nighttime. Thanks.
Today's topic is sir, shall we sign off now, sir? Shall we stop now? Screen share, sir. Screen is still seen here, sir. Integrating our system, like how and how execute the free group was. So shall we sign off now? Sign off now. Sir, sir. Thank you very much for your. And this approach is like so our theory is very easy. So this is therefore what is argument which is to the habit rule. So when we go to the real life and the whole thing works. No, sir. Can we stop for now?
Am I audible? Okay. So let me share the screen and let me know whether my screen is visible. Screen is visible? Okay, since I'm sharing the entire screen, I cannot able to see you. In case of any connection interruption, I request the organizers to call me so that we can fix the issue. Okay, thank you so much for the invitation. For the next 15 minutes or so, we are going to discuss about quantum computing and cryptography. So the agenda is that we are going to discuss how the computer works, and slowly we are going to introduce qubits and what is the difference between qubits and the bits. What are the key quantum properties, like quantum entanglements, and what are the pros and cons of quantum computing? Companies which is on quantum computing, which is behind the quantum computing. And we are going to see the difference between classical and the quantum computers. And we are going to connect this with the security. Because of the introduction of this quantum computing, how the security field suffers a lot. That's what we're going to discuss the inference. So how do normal computers work? You all know that normal computers works on bits, binaries. Have you ever heard that if a computer can do things regular computers cannot? Like now we are using systems, right? Desktop, PC, laptops. So have you ever heard of or imagining a computer which can do things which regular computers cannot? If you are not dreamt of that, now it has come into reality. Now we have these quantum computers which will do things which the certain normal computers cannot do. So these computers which can do the things which normal computers cannot do are known as generally the quantum computers. Why this quantum computer is superpower than the normal computers? Because as I said, the normal computers use bits for its working, whereas the quantum computer use qubits for its working. So then we need to know what is bits and what is qubits and what makes it more special and more powerful than the bits. You all know that a bit is like a switch light. The switch can be either in two states. Either it can be in off or it can be not. It cannot be in both states. It has been either off or on. So off is generally mapped to 0 and on is generally mapped to 1. So this is how the normal bits will work. But whereas if you take the qubits, these qubits can be simultaneously in both the on and off states. It might be puzzling how it can be, but that is how this qubit works. The normal bit either zeros and one, but in qubit, it can also be in both the states simultaneously. That is what the qubits is specialized in on. So you can take both zeros and one at the same time. Like whereas normal bits cannot take both the bits at the same time, it can be only in one state. So this means a supercomputer can do many things, and this is what this property which makes it faster than the normal computers. Why it is faster than normal computers? Because of this property that qubit can take both the states at the same time. It is like having many helpers working on a task. What if two people is working on a task? He may take 5 days. What if 5 people is working on a task? He may be taking only 2 days. The same thing happens in the quantum computing. Because of the property of the qubits, the quantum computers are much faster in solving the complex problems. So scientists generally, initially they thought about this quantum computers a long time ago, but it was only an imaginary phase at that time. But now it is no more an imaginary thing because we have quantum computers in place. So now people started working on quantum. We have the physical machine. Any concept at the start, it will be from imaginary, then it will be in the light. Like imagine 50 years ago, 5 decades, 6 decades ago, we will not know, we will not be that sure that computers will play a crucial role in everyday walks of life. But now imagine with the computers, we cannot even imagine it. So likewise, this qubits has been an imaginary concept for a long time, but now the concept has been coming to the reality because we have the computers now working on the qubits. So now companies and researchers are working. You know that government of India is making a lot of investments on the quantum computing. And you know how the regular computers works. So as I said, on bits. So since I said bits, you know the logical gates we might have studied in electronic circuits in UBE, like AND, OR, NOT, and XOR. These all gates takes bits as an input. They manipulate the bits on the circuit which is designed, and they will produce the output. So these gates, how we know, these gates are made only on transistors, and this is built on the properties of silicon semiconductors. So while classical computers are efficient and fast, but they have a problem. Classical computers means normal computers which you use, they have a problem. They cannot be able to solve a complex problem. For example, factoring a large number. That is what the main cryptography revolves around it. If you take cryptography, this factoring a large prime number is the biggest problem. It's a NP complete problem rather than we can say, because we given a large number, we cannot able to factor the large number into two different prime numbers in a matter of time. For that, we have to work a lot. Okay, this is called an NP complete problem. This is the behind of RSA algorithm also. And generally, normal computers cannot solve this exponential complexity problems in a stipulated amount of time. So now quantum computers comes into rescue to solve the problem, which is very, very complex in nature, and we can get the output in a shorter period of time. So on the other hand, quantum computers can come into the rescue because of these two properties. One property is called superposition, and another property is called entanglement. So in real quantum computers, qubit can represent in various physical systems. So like we have circuits, X, R, and not R. So in real quantum computers, we have qubits that can be represented by various physical systems, such as electron with spin, photons with polarization, trapped ions, and semiconductor circuits. So with this ability of this quantum computer to perform complex operations exponentially faster, the quantum to revolutionize many industries and to problems which was previously thought impossible. Previously, with the help of normal classical computers, you may think this problem is very tough to solve, or it is very close to impossible to solve. Now, this concept has been broken out with the help of quantum computers because of its capabilities. So it is not solvable in the normal classical computers. Now, these are solvable. And previously, which we think that in normal classical computers, it will take longer period of time to solve. Now it can be solved in a matter of time with the help of supercomputers. So what are the properties that make the supercomputer so powerful? The first property is known as quantum superposition. So qubits can do something really cool because they can be in the two states at the same time. As I said, an analogy, like it is like having two helpers working on a task instead of just one. So another analogy would be you toss a coin. In a normal scenario, we may think either can be a head or tail. But in supercomputer, at the same time, a coin can be in the two state. It can be in the head state as well as it can be in the tail state. This property is known as the quantum superposition. Yeah, at the same time, a quantum computing can exhibit two states at a time. So this is superposition. So this is the main property which helps the quantum computers to do many works at once. And this is where property which makes the quantum computer much faster than the regular computers. So this property is known as superpositions. And this is what makes it so powerful. So the ability of the qubits is to exist in multiple states at once and enables the execution of quantum algorithms and can solve certain problems exponentially faster than the classical algorithms. For example, in normal computers, if you take 4 bits, so how many different values 4 bits can take? So generally, it will be 2 power n. If n is the number of bits, the number of different values the 4 bits can take is generally 2 power n. It is nothing but here we have only 4 bits. So the number of different values we can have in 4 bits is nothing but 2 power 4. It is nothing but 16 different values we can have at the same time in the normal regular computers. However, in quantum computers, a group of 4 qubits can represent 16 combinations simultaneously. Now, the word simultaneous is very important. It can execute 16 combinations simultaneously. Why simultaneously? Because of the property of quantum superposition. Because at the same time, it can exist, if it is zeros and one, at the same time, it can exist in both 0 state as well as in the 1 state. So similarly, if we have 16 combinations, the 4 qubits group can be present in all 16 combinations simultaneously. That is what makes this quantum computing so powerful. This is one example because I have dealt with only 2 bits. I want to expand it for the 4 qubits. In 4 qubits, at the same time, we can have all 16 combinations simultaneously present in the qubit. This is called quantum superposition. So I want to state a couple of examples. This is a Gover's algorithm which we use for searching in unordered databases. So this generally, if you take this Gover's algorithm of quantum superposition, if we want to search something in a database, and the database is unsorted, unordered. Unordered means it is not in a sorted order. It is an unordered data set, and you want to search a particular element. Generally, it will take, if it is a normal classical algorithm, it will take n number of steps to solve the problem. Whereas if for the same problem to solve this searching an element in an unordered database, if we use this quantum computing, it can able to solve it in the square root of n steps. So what n almost half, square root of n means almost half, we can say. So with help of quantum computers, we can able to solve this problem in the square root of n steps. So another example will be the Shor's algorithm. So again, it is a quantum algorithm that can factorize the composite number in a polynomial type. So when I say this, this quantum algorithm can able to factorize a composite number, then it is a real threat to cryptography, because you all know the cryptography is strongly founded by the number theory. Number theory is nothing but founded by the mathematics. So if there is no number theory, there is no cryptography. If there is no cryptography, there is no security. The entire cryptography revolves around the factorization of a large prime number. Given a number, large prime number, we say that it is these large prime numbers into two different factors. But then with the help of the Shor's algorithm in quantum computing, we can say that we can able to solve, however large the number is, we can able to factorize the large prime number with help of this Shor's algorithm, and that too in a very short period of time. So these are some of the applications of quantum computing in the real world example. One I said for database, another for cryptography. So this algorithm of Shor's algorithm is having a strong implication on the current field of cryptography, because it is shaking the entire cryptography world, because you can able to factorize a large prime number in a matter of time. So when you're touching the base of any subject which is built on, then it will shake the entire subject itself. We know that nowadays internet is one of the basic needs. Whenever there is an internet, and definitely there comes the place of security. So security is a very evergreen field. And this quantum computing is shaking the entire cryptography field. So now the cryptographists are crypto analysts and the algorithm designers of cryptography algorithms. So they are now in a much worried phase how to deal with this. So the another property which we are going to discuss here is that quantum entanglement. So this is a very interesting property. Imagine that I'm giving an analogy again to understand the concept, because time given for me is very short. So I to make you understand these two properties in the short period of time. So I'm explaining with an analogy. Imagine that you have a two toy. One toy is a car, another toy is a boat. So if you put a car toy in one room and you put the boat in the another room, and make sure that they are friends. The car toy and the boat toy are friends. And you make them special friends, okay? This is the condition. So place it in one room, car toy in one room, place the boat toy in one room, and they have a strong relationship, strong bonding of friendship. Now, if you change something in one toy, if you change something in the car, the other toy also will change. If you change something in the boat toy, again the car toy also will inherit the same changes which is done in the boat toy. This property is known as the quantum entanglement. Okay, so even if you're not looking at one toy, you will be knowing what's happening at the other toy, because they are strongly connected, because we are very special friends. Whatever changes you do in one toy, it will be reflecting in the other toy. This is a connection. So because of the connection, the changes in one place will be reflected in the another place. You need not, for example, you're looking at only on the room which is having a car toy. So we're changing something on the car toy. You need not look what will happen to the boat toy. Whatever changes you do the car toy, it will be directly applied to the boat toy. So you need not look at the other toy itself. This is what quantum entanglement is called. It is like a secret connection between the qubits. So this is very real important properties of quantum computing, because it will allow us to perform certain calculation much faster than the real computers. And this makes the communication also so faster. This is a very special and powerful feature of quantum computing. So let's dive deeper into the quantum entanglement. So in other words, the state of one system is dependent on the states of other system, regardless of the distance between them. So however the two toys, which I said, how it can be in the same room in the same building, or it can be at two different countries, two different worlds. Never mind. You change in one, the state will be reflected. Change of state will be reflected in other things. This is what the quantum entanglement is all about. So now looking at the advantages of quantum computers. So as I said, the first advantage will be the speed. Like quantum computers can perform calculation much faster than the classical computer, making them well suited for tasks that involve large amount of data or complex mathematical calculations. And it also having the advantage of parallelism, and cryptography has the potential. So actually, it is a disadvantage, but I'm putting as an advantage. We will discuss that. So quantum computer has the potential to break many encryption methods currently used to secure the data. However, it also has the potential to develop new and more secure encryption methods. So it is like cryptography. We'll also used to say that there should be hackers. Unless otherwise, that should, if we are working in cryptography, you will always appreciate hackers, because hackers are the person who will try to always find faults in the algorithm, cryptographic algorithms. So unless otherwise hackers are there, our algorithms also will not be much secure. So this cryptography, since it's touching this quantum algorithm, since it is touching the base of cryptography, we will able to know what are the real hook codes. And it, on other hand, it will also help us to build a much secure algorithm in the context of quantum era. Next, it is also used in chemistry. So quantum computer can stimulate the behavior of molecules at the levels in detail that is not possible in the classical computing. So because of this quantum computing venture in chemistry field, what will happen? The drug discovery will be much faster. I think Sunil Raj sir is calling me. Yeah. Sir, tell me, sir. Hello? Yeah. Yeah. Thank you. Yeah. And having said the advantage, the disadvantage is nothing but noise and coherence, decoherence, and scalability are the disadvantage. Error correction, a lack of robust quantum algorithms, high cost and power consumptions are some of the disadvantages of quantum computers. And these are the companies which is working on the quantum computers like IBM, Google, Alibaba, Regidi Computing, Intel, DUA System, and Zenato. And these are the basic difference between classical and quantum computers. So classical computers works on zeros and ones, quantum computers works on zeros, one or both. And superposition and entanglement are not possible in classical computers, whereas it is possible in quantum computers. In classical computers, it performs only task, one by one task, whereas in quantum computers, we can have multiple calculations, you can do it simultaneously. And speed, quantum computers are much faster than the classical computers. And algorithms using classical computers is classical algorithm, whereas in quantum, we have to use quantum algorithms and applications. And as I said, because of this quantum computing, many of the cryptographic algorithm will take a new avatar, and that will be resulting in the short span of time. And this is what the short recap. So we started with how computer works. We see what is bits and qubits, and we have seen about various key quantum properties, quantum entanglement, quantum superposition, pros and cons of quantum computing. What are the companies which is working on quantum computing? And we also seen the classical and quantum computing differences and key inferences on the cryptography system. So I acknowledge the content and image are from various sources of internet and acknowledge the same. And in case of any doubt, you can reach me at this email, which is provided here. I am just concluded my talk. Over to the organizer. And this is what the email ID. If you have any doubts, you can always ask me. Over to the organizer. Hello.
Thank you, sir, for the it will be a very pleasure for me. It's a pleasure having you.
It is over.
Further,
Hi, hope I am audible to everyone. Yeah. Okay, good morning to all. Today, I'm going to give a short discussion regarding the how computer vision or image processing can be applied in the field of agriculture. So, I'll share the slides. Okay. So we can see the topic like vision to plant harvest. So how we can use the computer vision and image processing techniques in the agriculture industry. So basically, why this topic comes to a major role means India, especially based on the agriculture. So the major backbone is agriculture for India. And in earlier days, we had different revolutions. So one among them is the fertilizers. And then later on, the population keeps on increasing, whereas the production is not up to that level, which can feed that population. So the recent survey analyzed like the poverty level will be increased in 2050, but the increase in population keeps on like increasing in the exponential level. So because of that reason, we are expecting the food demand in the 2030 or 2035 itself. So in order to overcome that, in order to and also to feed the entire population, now the new revolution comes into the era that is called as the digital agriculture, where we have the different types of techniques, especially artificial intelligence comes into a major role in the field of agriculture. One among them is the computer vision and image processing techniques. So there are other things like robotics. I will share some websites where how other people are working in the end of the session. So before that, how a very simple and then effective uh, techniques which can be applied in the field of agriculture to predict the yield or to predict the parameters that can be useful in calculating the yield. So our main goal is to increase the yield and also to feed the entire population in the nutritious way. So the technique we are going to use is the plant phenotyping. So mainly it is used for the plant yield prediction. So what is in the plant phenotyping? So we are going to analyze the images uh, like we have taken the shoot image, root image, and then the leaf images. So different plant organs, the entire plant. So like that we can collect the different images, and we are going to analyze those images in order to predict the different plant traits. So what are the different plant traits? So here I have given some three like growth, shape, surface. So like canopy area, and then the temperature, and then other sensors useful to predict the other traits. So one among the main important thing is like a plant growth. So it is depends on the leaf area and then the leaf count. So that is the plant region. So that is the canopy area. So that means the leaf area, the canopy area. So in order to predict, if we have a single leaf, then we will go for prediction for the single leaf, but the plant has the entire leaf. So that is why we are naming as the canopy. If you look at the side images, given the single leaf as well as the entire leaf regions. So the entire leaf region mainly contributes to the plant growth, and the plant growth directly depends, the yield directly depends on the plant growth. So nowadays, we are measuring the plant traits manually, but recently many techniques has been used, digital agriculture techniques or the precision agriculture techniques has been used in measuring these traits using the artificial intelligence and other fields. So we have different fields like mechanical engineering involving in production of the machines that can be used in the field, agriculture field, and then the plant science departments also working on improving the techniques like genetically or else providing the different types of mutants. And then robotics has been the very emerging field working on this to control, doing it in the automatic way. And then the computer vision and image processing techniques for analysis, and then doing all the mathematical calculations. So these are the various different kinds of techniques now we are involving in these things. But in general, most of the cases, only the manual prediction has been going on. Now recently only we are developing these kind of plant phenotyping techniques. So what is the difference between the manual interpretation as well as the either the computer vision or AI based techniques? So the time is very less. We can do it very fast actually, as well as the error is very we can just reduce the error by improving. We have different types of techniques like deep learning, machine learning techniques that can be involved, and then so that we can train the model, develop the model, and train the model, and we can use it and predict or classify very easily what is based on our needs. So that is why we are going for using the computer vision techniques and image processing to involve in the field of agriculture to reduce the error rate as well as increasing the yield, and also the cost, especially the cost also reduces. So the very basic thing, I'm just going to deal with the very basic thing due to the limitations of time, and everyone can understand easily. So you all know that most of the plants are green in color, apart from few plants, some few colorful plants, and which has some different colors of leaves. Those colors of leaves are why the different colors of leaves exist. That is because of the anthocyanin present in the leaf, and also the different types of chlorophylls also are there. We have different types of chlorophyll like chlorophyll A and B. So I'm not going in depth into the plant science. Just we are going to see how that can be identified using in, our image processing techniques. So we are basically taking the color spaces for recognizing the plant canopy. That means we know most of the plants are green in color. So what are the, so here we have different types of cameras we can use for our computer vision process, that is image processing, to capture the images and for the data collection. So very simple and cheap camera is the RGB camera. So in thousands of rupees we can get it. Whereas the hyperspectral imaging and then the other kind of sensing, optical sensing techniques like Raman spectroscopy, fluorescence imaging, and monochrome camera. So those kind of cameras are like in terms of like lakhs and near half a crore or like around 40 lakhs, 50 lakhs rupees. And even Raman spectroscopy has different types like single spectra and as well as the Raman imaging. So those kind of camera is like more costly. It can be used in terms of a large scale industry, but whereas now I'm just making it as simple as possible so that how we can predict the canopy area, which we can easily identify using the RGB camera. We no need to go for the identifying those traits using the hyperspectral imaging. Where those hyperspectral imaging and other Raman spectroscopy comes into account means like early prediction of some disease or else some stress condition occurs, some environmental changes has been done. So those kind of factors can be identified using those kind of techniques like Raman spectroscopy and hyperspectral imaging. Whereas some of the traits can be easily identified using in the cheapest way. So one among them is the canopy area. So in this, we are going to see how RGB images can be used for predicting the canopy area. So it is like basically the prediction. So in general, we can just classify into two. One is the classification and prediction. Mostly it can be either in some of the ways, like if you know the deep learning techniques, you can just see the last layer. We can just change into the prediction as well as the classification using the softmax layer, and then directly by considering the probability that fit into the different classes. So it's a very simple thing I can just say. So mostly we can identify using prediction or the classification. In our case, it is a prediction. So we can just see what are the different color spaces before going into that. So initially we will capture the RGB image using any camera, or else you can use your own cell phone. But better to use the similar kind of like parameters, for example, focal length, and similar type of camera, and then the resolutions, so that your calculation is not going into the wrong different way. um, Now, if you capture the RGB image, you have the different planes, red, green, and blue. This is one of the color spaces. What is a color space? We are going to how we are organizing the colors into different categories. So from RGB image, you can convert to LAB and then CMYK and then HSA. There are different color spaces are there. So I am just limiting to only these two, RGB and LAB, for our analysis. We have done the many different analysis based on the other color space also, but now for this presentation I am limiting only these two, RGB and LAB color space. So R stands for red, green stands for G, and B stands for blue. And LAB means L is for lightness, and the other two components like A and B, that A stands for red and green, and blue, B stands for the uh, blue and the yellow. So I think it's visible for you, blue and yellow. And CMYK, and this L, right? L, it is like similar to how we usually interpret from our eyes. And also there is another color space like HSA model. So it behaves how our human eye our human eye visualize the color, different colors. That is based on the HSA model. And this CMYK is C for stands for cyan, M stands for magenta, Y stands for yellow, and K stands for black. We generally say this is a key, that is a black color. So this type of color space is used in the computer printer. How we print the whatever we have in the documents, we are printing, that color space is used for the computer printers. So this is and also other color spaces are there. So we are going to see RGB and LAB color space for our analysis. Now I will share the we can just go for the hands-on session, how we can use this color spaces and for predicting the canopy area. So all the machine learning, most of the machine learning, there are different types of techniques are there, like supervised and unsupervised techniques in the machine learning as well as deep learning. Now we are going to see only the machine learning part, a very very simple technique you all studied in your mathematics, maybe in the 11th or 12th, and how we can implement using that one, and how that simple techniques can be applied in the field of agriculture. We can easily identify that. Yeah, now I will we can go to the hands-on session. I will, as of now, I will stop sharing, and I'll share it again. I think the screen is visible. Is it visible? So already I have visible. Please let me know so that I can proceed. Okay. Already I have run the code, and so we are going to see in the two different way. Like one is the like each and nook and corner steps what we are going to do, and there's a basic core implementation. The another one is like importing the functions from the libraries, Python libraries. So this is a different thing we have imported. And the next thing is okay, so I am just keeping all the images in a folder in this path. So we have that folder named test, and then I am just giving all the in the name in the time. Either you can have a PNG image or JPG, whatever it is, you can just store it, save it in the folder. And I am reading all the images. If you can do one by one, I am just reading all the images in the particular folder. So that is this is the globe is the one which is we can use it for one. Many things are there. I'm just using globe. So this is used for reading all the images in that particular folder, and What are the types of files? It is like .jpg files, and star dot means all, it means all the jpg files has to be read. And then I am reading one by one, I am just keeping in the loop. And then at a time I'm just uh, say, I mean, just I am image img show one means, so if the loop comes first like 0 1 2 3, that means every time we go into the loop, one image will be uh, saved in that variable. And then I'm just transforming for uniformity, I'm just making into uniform size 256 cross 256, that x and y size. I mean, it is a RGB image, is a two-dimensional image that has three different planes. So that two-dimensional is converted to 256 cross 256 for the uniformity, because you may take images from the keeping the, if you have taking in the camera like horizontal way, vertical way, so the resolution, I mean the size may vary. uh, Keeping it as 256 to 256, and then I'm just showing the image whatever it is there. So if we look at this, uh, I'm just converting into RGB also, like R, G, and B. This is for separating the images. So this is like, I'm just printing one R. This is the first. Okay, so you can see this is the RGB of the first image. This is the tomato plant which I have taken in the like in the side of the fields. So this is the R plane, and then G plane, and this is the B plane. B plane. If you look at this uh, G plane, you can see the good brightness is there for the plants compared to the background, because when we just focused on the spectrum, if you have a R, G, and B, you'll be getting the peaks in the spectrum in the corresponding region. For example, R means it will be in the red region, and if it is in the G means it will be in the green region, and then we'll get the peak for blue in the blue region. So that is why here the plants are in green in color compared to the background. That's why the you can see the green color in G plane. You can see the plant in the highest intensity. These are all the grayscale images. Grayscale images means the intensity level starts from 0 to 255. So since the grayscale, I mean the peak intensities are peak for the green color in the G plane, that means the values from 0 to 255, it will be almost more than 200, or compared to the background, the highest values will be there. That means closer to 255, more than 200 or 225, something differs based on the green color. So that is what done here. Just once again. uh,
So you're on mute, sir. Sir, you're on mute, sir.
Okay, sorry, I was been muted. Okay, so we have different color spaces like LAB. I have shown you the LAB color techniques. This is like L, A, and B. So this is the A plane, which I are seeing, and this is the LAB color space, and this is the L plane and A plane, and then the B plane. So we can see clearly the L plane and A plane and G plane have the good impact for the green colors, and then we are going to use that for our and then B plane also for our segmentation. And for this we are going to use the simple thresholding technique, and then we are going to segment the leaves. So once we are segmented, we can just mask it, and then we can just take the a segmented image like this. So we have a very lot of different segmentation techniques, like in deep learning segmentation. There are many things are there. So this is a very simple technique we are using for segmentation, like a thresholding techniques. And then we got this. So from this, we are going to measure count the number of pixels, and then we are going to map it with our canopy area. So we know the biomass. I mean, the mainly thing is now we are going to predict the biomass. So for this biomass, we are going, there are different types of biomass. One is the dry weight and the fresh weight. Fresh weight means we are just cut the shoot and then directly weigh it, where that includes the water molecule also. Whereas the dry weight means cut the shoot and then go for drying the plant, and then deep freeze it under the -4 degrees, I mean under 4 degree or -4 degrees centigrade, and then deep freeze it and then go for measuring the plant. That means without water molecule. So that's how we are going to measure the dry mass. And then after this, we are just we got the canopy count, that is a pixel count, and we have the biomass area, the canopy area we have, and then the biomass is there now. And then we are going to use the train the model for our linear regression. So this we have the two different types. One is like this is the mathematical step by step how we can go for the linear regression, and we are calculating the how far the deviation about the x, and then the cross deviation about the x and y. So here the we know the formula, right? Y is equal to mx plus c, or y is equal to b naught plus b1 x. So we have to calculate the slope and intercept. So this is the coefficients, regression coefficient. This is the slope, and these are the slope and intercept. And you know, that is a b1 is the slope, and then c my is the intercept here. I mean b naught and b1. I mean we can directly say b naught and b1, and then we are going to predict the y, that is the my value for our linear regression. And after that, so once we predict it, we can go for evaluating our model, whether our model has been done or not. So we have divided into the number of plant sets into train and test, and the canopy area, and then the biomass prediction. And we have the intercept and slope values as 317 and 0.009. And we have this model has been predicted, and we have given the R squared as 57. So usually 0.5 to 0.7 means it is the model is performing well, but above 0.8 means it is a very good. Actually, the model above 0.9 means that is a very good, but best model we are getting. And then if you find out the RMS, it is like 24. Either we can predict the biomass in terms of grams or kilogram. If it is gram means if you can see like less than 5%, around 5% only the error rate in this case. So that means our model is performing well. And then if we look at this directly, we are using the okay. So we are going to wind up fast. So this is one way of doing like a step-by-step procedure, and another way is like directly importing the function from the, I mean importing the linear regression from the sklearn. So how we are importing, that's only one thing I will just show it. So sklearn we are just importing, and the linear regression, and in this we are just going to fit here the model. So here you can see I think it is scrolling. Yes. Okay. Now you can see the model dot linear regression. So we are just saying the linear regression model. You can have different types of multivariate analysis also, like PLSR, and then SVM, SVR, and different models. And then we can also train go for machine learning, other machine learning techniques. And like this, we are going to import the directly from the sklearn, and we are going to use it. And then we are calculating the model dot intercept here, and then the model dot coefficient. This is the b0 and b1. There is the intercept and the slope. And then after that, we are going to predict using the test X test means like the canopy area which we identified for the plants, and then we are going to predict the biomass prediction. This is the X test and the X value. So after that, we can just see I just changed the train and test data. You can see the R square increases. So if we change the train and test data, it keeps on increasing in order to keep the model like the prediction model works very well for the thing. So we have to use the k-fold techniques, like folding techniques like k-fold or a stratified k-fold. Different types of folding techniques are there, so that the model can be predicting well, such that even if you change the different train and test data, it will be working well. So I can just wind up as of now. Maybe if you have any clarifications, we can discuss.
Thank you so much. Hopefully you guys can hear me. Right, I'll start. I assume you guys can hear me. Do let me know if there is any audio issues. Thank you so much for the invitation. I'll share my screen and we'll start the presentation now. Yep. All right, so yeah, hopefully you guys can see the screen. Thank you so much for allowing me to do this presentation on the third International Conference on Recent Trends in Data Science. My presentation topic today is digital transformation in manufacturing, transitioning from industry, transitioning from industry 4.0 to beyond. So my name is Dr. Akhlaqur Rahman, or Dr. AK, as I was introduced. So I will skip the introduction. Thank you for that. Yeah, so my objective today is basically to give you guys a good idea about what is the current context of industrial revolution currently, or industrial automation, and where it's going, so that in the context of the theme, or the theme of the it's the current industrial situation, but also what to expect in future as well. So that's basically my goal for the presentation, to let you guys know where you are currently at and where you need to be going, basically. So as I mentioned, the objective is to talk about the digital transformation in manufacturing and talk about Industry 4.0, where we are currently at. Two Industry 4.0 and beyond. So let's start with a little journey of what is the current industrial journey, revolution, or where we are currently at. Hopefully the screen is moving and you guys can see it. So we start with a little journey of the industrial revolution, right? So when was the first industrial revolution took place? It was about 250 years ago, as you can see here, around the 1800s. This is where the first, around 1770s, that's when the first industrial revolution took place. And the idea was they managed to find the use of water. So how to find or how to channel the use of water for mechanization, essentially using water and steam power to run machines. That was the first industrial revolution. At that point, obviously, it wasn't called Industry 1.0. It was called the Great Industrial Revolution. People built industries around it where they found, okay, I can use force of water to drive a whole industry out of it, and then build cities and so on around it. Then around 100 years later, around 1890, came the second industrial revolution. Again, that was directed by what new technology came at that time. What was that? That was electricity. Electricity came about around 1890s, and that's when the second industrial revolution happened, where people understood they can do mass production using electrical energy. So instead of building one car, they can build multiple cars using multiple people in a conveyor belt, similar to a conveyor belt, like in an assembly line running, making same products, but in an assembly, like in a batch assembly. That was the second industrial revolution, and people realized, okay, I can use electricity for that sort of operation. Built a second set of industry. Again, about 1970, 50 years or almost 60 years from now, before now, around that time came the third industrial revolution, which was aided by the innovation of computers. So people saw that, okay, using computers, I can control machines. I can manually control the machine with PLC and automation. That's where the production automation came, and people built industries around that. So using computer and IT technology, they could control machines. That required people who were doing manual labor to train and basically started learning how to use computers so that they can control the machines. And about 10 years back, or around basically the last decade, is where Industry 4.0 came. That was the digitization of the factory, which is our theme for today's presentation. That was aided by the innovations of, technology, IoT, or Internet of Things. Essentially, what people realized was with cyber physical systems, I no longer have to be on the plant floor doing a lot of the manual work. So instead of doing basic sensor checking and control, temperature control, and that sort of operation, why don't I automate the machines? They can communicate among themselves. I can monitor it from a higher level. So all these people who are working the board, now they needed to realize how to operate and design the machines in a way so that I can actually control this operation and supervise it from above. So with each industrial evolution, what's happening? There's a new technology and it's taking the their skills and learn new technology so that they can adapt to what is what has come and basically move on to these new roles. So essentially, this is what's happening here, and this is where our current context is. So this is what we are at, Industry 4.0. It's a new phase in the industrial revolution where you have intelligent networking of machines and process with the help of information and ICT. Essentially, world is cyber physical. So it's in the cloud, for example. So you have technologies like IoT, advanced robotics, obviously AI now, the biggest part. You have cloud computing, big data, cybersecurity, additive manufacturing. All these are integrating together to make the operation more smoother than ever. But essentially, when does the role of data science come into play here? So for example, all these operations require huge amount of data to be sent to the cloud so that it can do a lot of computation over there. So things like predictive maintenance. So machines can analyze models to predict equipment failure. You can optimize process through data analysis, quality control through computer vision, or supply chain analytics to predict demand, optimize inventory, improve logistics. Those are the ideas. So this is what we are currently in the middle of, and we are still progressing through it. And that's the idea. So if you look at some basic information about Industry 4.0, it is now being applied in almost every industry. You can see 7% in aerospace and defense, your medical devices 6%, communication 3%, but obviously things like industrial products and automotive 12% and 26% and 12%. So there is a big shift in the industry for or industrial auto applications especially due to Industry 4.0. In fact, the main theme for today's presentation, which was the digital transformation of manufacturing, if you actually look at it, what is actually happening is they're using technology and automated system to perform various tasks with minimum human intervention. So the whole focus of Industry 4.0 is to move people away from the presentation flow, or rather plant flow. So here, with the help of automation and design, determining manufacturing equipment, designing the production layouts, developing the necessary software and control logics, even more with the raw materials, more automated handling of the materials. Everything now individually are obviously more automated, but they're also integrated as well. So if a production needs to be customized, a lot of the design can now happen in real time rather than having to wait for the next batch. So these are a lot more fluid, lot more smoother operation. The whole manufacturing line has become a lot more fluid, which is the main idea of the presentation today. Now, why I'm talking about this is just so you guys can get a bit of context about how digital, what is the current context in terms of in the industrial revolution. And obviously, I already talked about the role of data science in it. Now, the benefits here, as you can see, more scalability, more security, operations being more secure, there is a more control and visibility. So you twin helps. So again, these are all possible because of data science, because that's a big part of Industry 4.0, where huge amounts of data are being processed in real time, and analytical support, analysis, computer vision, these are allowing things to happen. So that's the idea. So you see things like industries already using it, like ABB Smart Robotics. Can be done in accordance. You have Fanuc, which is a robot maker. They're using sensors again with cloud system and process equipment. So that helps with the process optimization. You have KUKA robots. There you can see they're the German specialist who has an IoT strategy, and previously they could churn out one car body in every 77 seconds, and they were asked to do that. And with IoT enabled factory, now they can do 800 vehicles in one day. So that's how data driven the technology is currently, and efficient as well. You look at even a mining sector, you have like Rio Tinto, who are actually using autonomous drill technology to again do mining in the mining site for more safety purposes. But again, these are driven by data science and the progress there as well. You have things like Shell, who is using digital twin initiative, which is again big data being processed as well there. So these are all examples of industry that are actually using modern technology and Industry 4.0 currently in practice, which is hugely aided by the cyber physical systems, where the cloud to physical data communication and the data transfer and analytics. Right. So obviously that probably would have good knowledge about, and hopefully you guys are interested in and will be a part of it in, or already are, or will be in the next few years. But what I also wanted to do was take this opportunity to discuss about what's coming up. So as upcoming engineers would also, need to be aware of, obviously. So that's where I wanted to discuss a little bit about the next industrial revolution, which is Industry 5.0. So Industry 5.0 is a new model of industrial development that aims to embed human, social, and environmental values at the center, so major technological innovations can happen. Essentially, to summarize in a very short time, I have only 5 minutes left, I think. Okay, so if Industry 4.0 was about taking people away from the plant floor, so machines can operate on a plant floor in an auto is about bringing humans back into the operation floor or plant floor, but in a safe manner, and keeping the focus of human safety and as well as environmental safety. So that's mainly Industry 5.0. Essentially, what I mean is, in Industrial 5.0, there will be two main focuses. One is human-robot co-working. Essentially, instead of humans, now they will be back in an operation floor. For example, like this, if you look at a plant layout, say co-boss, collaborate, wearable technology like exoskeletons and other sensors that will help them with improving their efficiency, and all the operations, they will be individually like modular in nature, but they will be well integrated throughout. So communication will be much faster. Computer vision technology, you will to be much more easily available and better part of the industry in the next decade. The interesting thing about Industry 5.0 is, although 3.0 to 4.0 took about 50 years, they are predicting 4.0 to 5.0 won't take that long. Some people even suggest that we are already partially in 5.0, where 4.0 and 5.0 are overlapping with each other as well. So that's one part. The other part is the bioeconomy. So what bioeconomy by that I mean is renewable will be a big part of Industry 5.0 as well as sustainability. We use these terms quite a lot, but they are actually quite practical. So essentially the idea will be in Industry 5.0, humans will be a big part. So that's why people centricity. Sustainability will be a big part. So let's say an industrial operation will be designed in such a way the residues or the wastage of the operation will need to be recycled into the operation itself to make sure that they make the process a bit more sustainable as well, and also more renewable technology will be used. The other aspect is resilience, where it means that they will be a lot more dynamic in nature. And this is where data science will be playing a very big part. Where in Industry 4.0, data science was helping with predictive maintenance, process optimization. Here, data science will help one with human and AI collaboration. So AI analyzes data while humans make. For example, data analytics will help companies with produce more customized products in real time. Sustainability optimization. So for example, data science will analyze energy usage, carbon emission, resource consumption. It's essentially the current technology, but the focus will be heavily on there, and more resilient system, as I mentioned. Supply chain will be able to be a lot more thorough and will predict disruptions a lot faster and adapt quickly. That is essentially the idea. So if we look at some of the pillars like industrial blockchain, mixed reality, I would say 6G, not 5G, more additive technology, drones, exoskeletons, these will become more bigger commercial part in the next decade. That's why they are expected to be the pillars of Industry 5.0. So if just quickly summarize what is the difference between 4.0 and 5.0. If 4.0 was essentially about data science to automate and optimize the machines, right? So in factories and sensors, they would be doing that. In Industry 5.0, the idea is you're using data science to support. So things like more customization and personalization, a more circular economy, and humans having a more central role in Industry 5.0. That is what Industry 5.0 is expected to be. So that's something as future, scientists and engineers, you guys can look for.
informations from data using machine learning concepts, right? Working together, we have to quantum computers based on this based on this classical computers only. So normally we know that the 5 generations of computers are there. So here, first generation computers, it focused the year that is 1946 to 1959. So it is based on vacuum tube based, and second generation is based on transistor based. It's replaced all the vacuum tubes in the year of 1959 to 1965. So here, this first generation computers, it is called, like we know that ENIAC, that means electronic numerical integrator and computer. So these are the first generation computer. So second generation computer is based on transistor based. So it transistor only replaced the vacuum tube. So we have smaller, that is every process speed of these things is so it's transistor based only smaller size, computer size is very smaller, and it is a faster one, and we have to get that efficient computation here. So third generation computer is based on integrated circuit based. So in the year of 1965 to 1971, so we have this third generation is basic, that is beginners all-purpose symbolic instruction code. So here this integrated millions of data, that means ICs means you have to incorporate all transistor, resistors, capacitors, everything ought to be incorporated into a one single chip, that is called ICs. So third generation computers is based on ICs, and fourth generation computers, it's the VLSI microprocessor based one. That is very large scale integration based computers are there. So here all the millions of components are integrated on a single chip. That is very large scale integration. That is fourth generation computers. So this semiconductor is based on RAM on ROM. That means read-only memory and random access memory. So this memory storage is basically random access memory and read-only memory. So fifth generation computers are based only that AI concept, that is, or it may be called ULSA, that is ultra large scale integration method. So it's parallel processing method. So here this AI only, we have to use quantum computing and machine learning. So it is advanced computing technology. So first generation computers, it's look like this very large size. Second generation computer is basically transistor based. So it replaces all the vacuum tubes, but it has the speed of processing is very fast comparing to the first and second. So third generation, it is a little more fast when you compare that second. So third generation computers, it's basically only IC. So it's very compact size. So fourth generation computers, we already know this. We have to introduce the multi-programming concept, multi-processing concept, and multitasking and time sharing methods are there. So here fifth generation is based only the AI. So with the human interaction only, we have to do the actions. So it will just behave like a human, and what we think, it will implement our actions, right? So next, this technology is based on nowadays that is future technology is based on the quantum computer only. So it will machine that will perform some calculations based on the laws of quantum mechanics. That means the behavior of particles at the subatomic level. So it's based on the quantum atomic level. Next, when you compare the classical computer with respect to the quantum computer, so quantum computer only, it uses the voltages flowing through circuits and gates which use principle of digital electronics that will perform some operations like this is the transistor based thing. So how to positive terminal is to be connected with one end and negative terminal is connected to the ground. So likewise the transistor is to be involved in this third generation only. So this is the classical time. So it's based on only circuits and gates. So this is the quantum computing. This concept is introduced by this persons, David Jeffrey Wineland and George Courage. So he is only awarded both are awarded with the Nobel Prize for this work, this quantum computing. So it's measurement and manipulation of individual quantum computing. In the year, so in the upcoming year, that is focus from 2012 to 42. So this is the person. He is the his name is Gordon E. Murray. He is the electronic engineer. He studied BS degree in chemistry and from the University of California and got the PhD degree in physical chemistry from the California. So he is only the director of this semiconductor field. So so based on this Moore's law only, we have to check this future size with respect to the number of chip components. So here, according to that, future size is from 10 power 1 to 10 power minus 3. So when the number of microns is to be increases with respect to the number of chip components. So based on this future size is to be in the year of after 2012 only, that is in the year of 2000 up to this 2040 only this age, that is quantum age is declared in this period only. That is according to the number of size microns increases with respect to the chip components, right? So this based on the Moore's law only we have to define this quantum age with respect to the classical age. So number of transistors is to be double after the 8th month or 2 years. So number of transistor on a microchip doubles approximately every 2 years. That means driving exponentially growth in computing power. So this is the classical bits. How can you represent the classical bits means? So here normally classical bits is represent zeros and ones with respect to the classical computer. So it is encoded in binary numbers of 2 bits and you have to perform the computations and you have to achieve the desired results. And based on the transistor only, we have to work reliably and it have some binary bit based devices like computers, mobiles and other devices. It has the label operations. So let me discuss some quantum physics. What does quantum physics means? It's based on only quantum theory. So it is the branch of physics only. This is the physical phenomena, right? So this atomic or a subatomic scale only we have to define it, and it only the accurate description of the behavior of photons, electrons and other atomic and molecular scale objects, and we have to describe description of reality at that scale only we can define this quantum physics. So next one, what is the basic elements of this quantum physics is before quantum mechanics we have to define it. We have to discuss some 5 parameters. So one is wave particle duality and discrete quantum states and discrete quantum states, well-defined spin, and measurement determines reliability. So next, quantum physics is not a magic one. It is energy conserved. Once the entropy increases, then the speed of light is also exceeds. So based on this, we know that if you toss the toss the coin, means it has both states, right? So that is tail as well as based on this quantum states, you have to define when you toss the probability of whether it is to be head or tail. So different quantum states is to be there for you have to analyze the discrete amounts. So it define the quantities that will described in the form of quantized that is quantized amounts. So it has some definite spin which gives the momentum and orientation in a space, right? So these are the quantum bits. How do you define this quantum bits? Means
Yes,
you
ma'am.
have, yes, sir.
And can we conclude it, ma'am? Sorry for the interruption.
Okay, sir. So I will conclude it, sir. So,
Thank
so proton and electron is a qubit here, and quantum bits you have to based on the digital information normally zeros and one. So quantum bits is only the quantum states based on this formula you have to define it. So we have to define the travel salesman problem is one of the examples for it. So how we can analyze the problem, how to solve the problem using quantum computer, and based on the already morning the sir told that how superposition and entanglement process is there using the quantum computers. So here the based on this concept only, this quantum computer can work. So it is the quantum particles, entanglement, and superposition. It has multiple values. That means simultaneously you have to execute the data. And this is that superposition process is there. So it describes multiple possible state at the same time. So here this one example of superposition, how it work with this principle based on this experiment. So this is the process of entanglement. So this process is based on that only spin of its partner in this opposite direction. This phenomena is called entanglement. So here this is one how we can spin it from upward direction and downwards directions. So what is the power of qubits? How can you calculate with using this supercomputer? So supercomputer is only the main powerful component for this one. So this quantum states is based on that is not gate. So in this unitary concepts only, we can, this is the structure of the quantum architecture based on this J gates and E gates. Then how data is to be encrypted based on this working principle. So with the RSK algorithm. So this is the applications. What are the applications for this quantum computer? Is factorization and physical modeling, simulation, and database searching. These are the some of the applications we can use this quantum computer concept. So DB concept only. This will use the pseudo puzzles, how to solve this puzzle manner for this using this quantum computer. So this is the D-Way concept structure. So based on the summary, I will conclude it. So here, every time we can add the qubit for computation power is increases based on the quantum computer. And so quantum computers only, we use the qubits, whatever the data operation we can perform it using electron and proton is act as the qubits here. So I concluded, this is my summary of this one. So quantum physics is introduced by this Albert Einstein only. So thank you.
Thank you, ma'am. Am I audible? Yeah. Good morning, everyone. So it's my privilege to join for this conference to give a small speech on it. So it's my honor to give the session on AI and data science in the future perspective, how we can go ahead in the future. So as we could see here, where we are today. So most of the companies nowadays, and when we talk about AI/ML, 97% of the companies, they are working with AI/ML. This is a scenario which was conducted in 2025. When we see the analysis of AI with the data science, so nearly every day, near about 2.5 or we can say to 25 lakhs gigabytes of data every day collected in globally. So how do you handle it? How do you process this data? How do you handle it with the AI? How do you help it with the AI? So we could see how it can help it in the future. So more than 10 times faster we have to work on. So for that only we are moving with AI. So AI is moved from experimental to the data to essential part of the life, where we can use machine learning, deep learning, natural language processing. These are all playing the very important role in the years where the research work is happening. So before starting with the challenges and applications, first we should know how does it relate each other. So there are three things which we should know: data science, AI, and machine learning. How these three are related. First, let's see, there are three layers. Just you imagine these are the three layers. The bottom layer is data science, and the middle layer is machine learning, and the top layer is the AI. So data science means what we can say, it gathers and cleanses and organizes all the data, whatever we have. And the machine learning part, what it does, it finds the patterns from the data, whatever we collected, and it performs the statistical analysis and whatever the model we could able to apply. So that can be done by the help of the machine learning. Once machine learning performs, then finally we can apply our AI model. So where those patterns, whatever you extracted from the machine learning algorithm, so that will take it into actions automatically. For example, when we see the hospital, data science means it takes the records from the hospital, and ML means it finds the patterns from the data, whatever you gathered. For example, when we talk about the heart disease, it can gather the data about the heart disease people. And finally, the AI automatically finds the patterns, whatever is there in related to the patient's prescription. Accordingly, it will react and gives the output to the doctors. Accordingly, the human being can decide what to be the result. So that we could see here how they intersect each other. So first, data science provides the necessary foundation or the infrastructure and the raw data. Then machine learning, which acts as a bridge here, and if we can apply any statistical model and any algorithm, we can apply. And finally, we can learn the model and you can take your decision, or we can say automatic decision, we can take it by applying our model over here. So here we could see what is the difference between all the three: information, knowledge, and intelligence. So first, whatever the data you collect, that means, for example, we could see here the raw data, that means tweets, sensor data, whatever the data, raw data, it is available. By that, we are collecting the data. And then information means the process data. One example I can tell you, suppose if we are taking the reading by the help of thermometer, suppose if I say 38.5, just it is a number. When I say 38.5, it is a data. When I say it is patient John, 45 years old, and the temperature is 38.5 degrees Celsius at so and so time, that means we can say it is a information. If I say patient with this temperature and the age is 45 years and the risk is very higher. That means I can say the patient is in a risk period. That means it is in the knowledge. When I finally say it automatically alerts the doctor and prepare the treatment, what to be done, that is intelligence. So how does it differentiate each other? That means initially we are collecting the data in the raw form, then it is processed, that is information, then we are finding the knowledge, then finally automatically whatever the action you take place, that is called as intelligence. So these are the key AI technologies which are driven by the data science. What are these most of us are aware of? So one is machine learning, then deep learning and NLP, natural language processing, and LLMs, and auto ML, generative AI, and explainable AI. We could see one by one. So when we see machine learning, this we all are aware of. Machine learning is the foundation of everything in the day-to-day life. Nowadays, people are working with many machine learning algorithms. What it does, it automatically discovers the patterns in data and improve their predictions over time. So what we see, we first collect the historical data and we identify the statistical patterns from that, and we build a model. Once the model is built, we can generate the predictions for the new and unseen data. So these are the three core pillars of it. So one is automated model building, feature engineering, and predictive analytics. So these are the different pillars. Like first, automated model building, what it is doing. Like algorithms, we can apply linear regression, random forest algorithm, gradient boosting, and support vector machines. So these are the different algorithms where we can apply and find the relationship between the data where there is no hand-coded rules. Then second core pillar, what we can say feature engineering. So what are the features we could able to select? So which feature if we select, how does it give you the better performance? How does it give you the better accuracy? So what are the features to select? That also we could apply the machine learning algorithm. Then the third one, predictive analytics, which model you apply. And according, for example, if you take see stock prices and if you see the equipment failures, so according to your historical patterns, how do you take your predictive analytics? How do you do it by yourself? So for one example, I can tell you Netflix recommendation system. How does it happen? It was not programmed how the rules look like. Suppose if I say number of action movies have come, show their actions. So instead of doing manually, the ML can learn from the millions of users what are their habits and how the patterns they are owning. So by that, the machine learning can give the final actions. So this is a way how machine learning works. So these are the few real world uses. One is spam filters, credit scoring. We can find out fraud detection, recommendation engines, predictive maintenance, and we can go for diagnosis. Any disease diagnosis, it can be detectable by the help of machine learning algorithm. Next one, deep learning. Deep learning, where in ML we are not seeing the hidden layers. Here the main thing is we could see the hidden layer here. So once you give the input to the deep learning model, there are hidden layers where it processes the data and gives you the output. Suppose you see the example here. These are the different inputs. How does it handle? One example, we can see X-ray. When you see X-ray, when you are applying the deep learning model, first what AI does is it see the edges and the lines. Okay, then this next layer. Suppose if we say there are 4 layers, the second layer it see the shapes. How does it look like? Then third step, for example, when we talk about the patient's images, then it belongs to which organ it is talking about. Then afterwards it identifies what are the abnormal tissues from that particular image. Then finally it gives how the probability of the patient, whether the patient is having malignant or non-malignant. So we can identify from that. By this deep learning model, the work can be better. So these are the few things which we can see here. One is by considering the image, CNN model, convolutional neural network model can be applied to detect the tumors in the medical scan, and the power face recognition also we can apply in the self-driving car to see the visions. And when we see the text words, we can learn the grammar, sentiment analysis we can do by considering the billions of words. We can take huge data. LSTM models you would have heard, where we can apply all the more or billions or millions of data, where we could analyze the stock prices, sensor readings, and the speech we could analyze by the help of deep learning model. When we come to the NLP model or LLM's model, NLP is, which is natural language processing, LLM is large language model, where AI that understands the human language. Instead of doing manually one by one, we can do by the help of natural language processing, where it can handle natural language querying. So natural language querying means in our DBMS or SQL query, how do we do? This is the way how we fire up the query. Like if I want to see the top 5 products in the last quarter, so we write a query in the SQL, select product name, sum of sales from orders, where so and so, group by product name, order by sum of sales in the descending way, and it is limited to 5. So, but when you see AI, you just write a question, what were the top 5 products last quarter? So it gives you the final answer. So it reduces your time. So that's what written here. It reduces it works with the natural language querying, text classification. For example, if I want to classify the emails or I want to classify the reviews, that can be done by the help of natural language processing. And then summarization. If we want to summarize maybe 100-page reports into one page, that can be possible by the help of NLP. And sentiment analysis. Suppose if I want to see the feedbacks, whether it is positive or negative, accordingly, whether that product can be sent in the market to do the next selling. So to do the analysis, we can apply this NLP things. And LLM model, actually, we all are aware of large language model, where ChatGPT, Claude, and Gemini are using LLM models. They are trained on trillions of words, where we can able to predict whatever the prompt you are giving. It could able to generate the human language with a remarkable fluency. So what are the things which are possible by the help of LLM? We can generate the codes, we can generate the reports, and we can create the mails how the user wants. That means document parsing, information extraction. These are the different things we can do by the help of LLM models. So next one, AutoML. So AutoML, by the word only we can understand. Instead of doing machine learning one by one, this does it automatically. Instead of doing one by giving the model and getting the output, this does it. The algorithm is fed automatically. That is what it is written here. Democratizing model development, making data science accessible to everyone. So this is inbuilt. The main, one of the famous tool, that is H2O.ai, which plays an important role for AutoML, where instead of doing traditional ML, we can apply this by the help of the skilled data scientists. This has been developed, and main domain experts like doctors, engineers, they are using. By applying this model without knowing the coding skills, they could able to do it better. So next we could see the next type, that is generative AI, where you can create the new content by the help of data, text, images, and code. It is not for classifying or predicting. We could able to create the synthetic data. There are 4 things we could do. One is synthetic data generation, data augmentation, intelligent report generation, and code generation. So first, when we see synthetic data creation, suppose for example, I can say, most of the hospital nowadays don't give the data, where the data is very privacy. It is maintained in the hospital where nobody can share their data. So due to the privacy laws, that time we can able to create the synthetic data. That means, for example, if you want to create 1 million fake data, but it should be the realistic one, that can be done with the help of synthetic data creation. Suppose when I say data augmentation, it expands the training data set by generating the variations, for example, by considering rotated images, or you can do it by paraphrasing the text, or you can do it by time series if I want to do perturbations. That all can be possible by the help of data augmentation. For example, if I have 500 X-rays of a rare disease, and if you want to do augmentation of 10,000 more images, that can be possible by the help of the data augmentation. Then intelligent report writing. Suppose if I have a, automatically it can produce the written summaries of the dashboard, results, model outputs, and the trend analysis, where you can convert the raw numbers into the readable form. So this is mainly helpful for the sales point of view. It can be used for the report generation. If you have, instead of just saying 20% of product sales dropped in Mumbai, instead of saying that, if I want only in Mumbai region and how does it reflect in the quarters, we can write it report generation perfectly. Then code generation, suppose tools like GitHub and Copilot, which can help the reduce the coding, and it can generate the code for us, and it can reduce our time. So next one, explainable AI. So here, first at the left hand side, we could see why the XAI is critical. Why? Because it can have a bias detection, trust building, and debugging model. So how does it say bias detection? Where it reveals when models discriminate unfairly. For example, it can hire the model that penalizes the women, or a credit model that disadvantages the minorities. One example I can tell you, maybe in US, by considering the old data, that means whatever the data which they have saved as historical data, the black and the white people. So because of that old historical data, it was that because of the trained data, whatever was available, the AI was giving the wrong prediction that the black people given the less treatment compared to the white people treatment. So this kind of misleading can happen if you give a wrong data while giving the training. So that should not happen. Then trust building, the doctor won't act on a diagnosis they can't understand. So, and one more thing, the loan officer won't approve the AI decisions without knowing the reasons, because there is a model called black box model, where we cannot see how does it work inside, just it gives you the output. So we could see it here, the black box AI. So how just you give the data which you are giving it as an input. So nobody knows what happens inside, just it gives you the output, what the answer comes out. So the doctor cannot understand what it does, the processing, how it is doing it inside, doesn't give you the process, how does it happen? That is what black box AI. So there are models, there are models which are available where we can re-educate this black box AI, then we can do better. These are the few models we'll see later. So these are the three critical things. By this three different XAI technique, that means explainable AI techniques, we could do better. The first one is SHAP values, that means shapely additive explanations, where you can see each feature's contribution, how does it work with the prediction. And line model, it is local interpretable model agnostic explanation. It creates a simple, locally faithful prediction where anybody can understand. Then attention maps, where you can see a words or image regions, the model, how it is focused to take the decision. So here we could see SHAP, shapely additive explanation. How does it do here? So A just gives you, suppose if you are applying for a loan, A just gives you, by taking the data, just gives you the output, bank loan is rejected. But when you see, when you apply through SHAP model, it gives you the reason also, by considering like a base approval chances, so and so, by considering all the scenarios, why it has been refused or why it has been rejected. So this is some of the scenarios given here. Suppose when we see the cancer risk, without SHAP, just it gives you 87% the chances are there, but it doesn't tell you the reason why it is. But here with SHAP, it gives you, because of the age, BP, and the family history, it is giving 87% chances. And loan rejected, why it is rejected, there is no reason. But when you apply this model, it gives you whether what is the debt ratio and what are the missed payments you have in your CIBIL score. So accordingly, it gives you the justification. Suppose next example, machine failure predictor. So it will fail if you give this so and so input. But without reason, it gives you. But when you apply this model, it gives with the reason. Same way, doctor's test, it is a no without SHAP, and with SHAP model, you can verify and trust. Same way, when you apply the line model also, how does it give you the output? With the line model, without line model, how does it? Just nothing will be given. But with line model, how the risk is, we can predict by the help of this model. So next, what are the challenges and ethical considerations while doing with AI and data science? These are the different challenges. One is data privacy and security, explainability gap, data quality, bias and fairness, talent shortage, and infrastructure costs. How does it apply? So when we talk about the data privacy, so this all we are aware of, mainly with the health sector. How does it apply? So what is the challenge we are facing? So when we give this patient data to our AI, and how does it take the data? As we are working with huge amount of data when we consider the hospital, but patient data is very secured, it is private. Using it without concern or proper security, it violates the people's rights. So how do you solve it? So techniques like federated learning, like let AI train on the data without ever seeing the raw patient records. It can save on their local servers. It is how does it work, this federated learning? Instead of collecting everyone's data in one central server, which is risky, that means anybody can take out that data. So this AI model will be sent to the hospital. Each hospital trains it locally on their own data. Only the learned patterns so AI still. Yeah. So these are the different things. One is bias history and how does it work with AI? How does it deployed in the clinic? These are the unfair things which could happen. So this is how we are giving the input. When we apply the black box AI model, just it gives you the output. So black box model, without knowing it, it does. So nobody knows. Yeah. Yes. Yeah. So this is yeah. So this is data quality. When you give the good data, it performs better. If you give the bad data, it doesn't give you the proper output. So this is reflecting in the infrastructure when as we use the GPU for training AI models. So it is more than around $100 million it is occupying. So same way data storage as well as cloud hosting, it is taking a lot of price. So these are the few applications where we could apply: healthcare, finance, and manufacturing and retail. So healthcare, how does it? There are three things which you know. It learns from data. It finds the hidden patterns. It finds it very fast. So these are the different things we can do in healthcare. So this is one of the example, one case study we have taken. So one is how does it? It takes the scan data. It scans through AI. It searches for the clues whether they are having the patient is sick or not. It flags the suspicious areas and finds the final result. So same way, the one more case study in US. There is a disease called sepsis. So that treatment has to be given immediately. By considering AI, they applied with the patients. Every 15 minutes they watched or they see the scenario. So by that they reduced 20% of the fewer deaths by the sepsis disease, and 38% emergency cases only there, and 6 hours they gave the early treatment. So these are the advantages: speed, accuracy, and it is can be applied at 24/7, and we can handle the big data. The challenges are privacy and bias handling. It cannot explainable why it is taken, and it is more costly. So this is the small knowledge you can test. How does it apply with the AI and data science? So this is with the help of the AI. The accuracy is better than the human average. So how does it take it traditionally without AI? Maybe 13 to 20 years if the patient without AI, if we do the analysis. And AlphaFold, how does it predict the 3D proteins? It helped the doctors. AI cannot fully replace the doctors. Always we need the doctor's help. So this is what we learned from the slide. And thank you, sir. Thank you, everyone.
Thank you. Thank you for the welcome. Okay, let me introduce myself. As they mentioned, good afternoon to everyone present here. First of all, I would like to sincerely thank the organizers and the Department of Data Science for giving me this wonderful opportunity to speak at this third international conference. It's truly an honor for me to be here as a part today. And before I begin, I briefly introduce, I'm Lakshmi Devi. I'm working as a data analyst at SRM Group of Institutions, handling both Chennai and Tiruchirappalli campuses. And it is inspiring to see how this conference continues to grow ahead. And thank you, organizers, for inviting me once again. Okay, I don't take much time. I'll dive into my topic. Let me share my screen, please. I hope the screen is visible to you all. Thank you. Okay, I'll dive into the topic as the rise of unified analytics platform, which is, I know you may guess it right, as an analytics platform, which combines with the integration of the analytics platform as a data science end-to-end frame. As the data is generating, growing as a rabbit in time, if we take some any industry or organizations, they collect a random of data. They don't know how the data is coming in daily, day-to-day basis. So the advanced analytics takes place, and we move on to the multiple systems what we need to adopt it so far. But the organizations struggle to convert the data, how we are going to use the tools and platforms as in one data frame. I mean the end-to-end data frame. As you all know, now we are using in the basis step of, in the first step as data feeding, then the data processing as the data, what the data engineers do, and you go on with the predictions or what else, what's it, then you move on to the business intelligence tools and so on. Am I right? But you're using separate tools, which is in the isolation mode. You'll rely on one tool for data ingestion, and for data storage we have to manage the dbms for it's based on the rdbms or non-rdbms. Okay, am I right? Then we will move on into the solution part. As the prediction system, will rely on some any coding platform. Then for presenting in the visualization manners, we'll move with business intelligence tools. With this, it will create the data silos. That means the redundancy is created so far, and it takes more storage on each tool. And finally, the architecture will get complex in structure. So nowadays, the organizations move from the isolated tools to integrated platforms. I'm sure From now to the future 5 years, there will be a great boom in data science with these integrated tools. I'm sure about this. Now, so far we have used with traditional analytics with individual platforms. Then we moved into big data ecosystems like Databricks, data lakes in separation. Now, the organizations and the modern industry is coming to use with a modern unified platforms, which I'm coming to say is unified analytics platforms. For an example, it is for a great example, you can assume or you can utilize Microsoft Fabric. I know, I don't know how many of you came up, no, across this word. So earlier, the analytics focused only on the individual tools, as I said earlier. Now it is an emergence to use only the unified analytics platforms, which is an integrated platform where the all the role of data science teams can use, from the data analyst to till the end of data scientist. The whole professionals can use into these one integrated platforms. Now, coming to the main part, what do you mean by unified analytics platforms? It's a completely single ecosystem where the storage method is considered as one lake, which is a unified storage system. You just go on research about it in the Microsoft Fabric, which is the amazing platform where we can utilize a lot, from the data ingestion to till the output, or what you have to provide with to the clients or the industry organizations. It has the high governance and security operations. We can maintain the high provide maintain roles for each security persons and managing roles. This is the Microsoft Fabric platform architecture, where it operates with the IQ platform too, where we can use the AI transformations and the data with the semantic models too. I know you hope with the semantic models means in the normal data set. Semantic models, along with their architecture, we can connect with the whole integrated platform in the Microsoft Fabric. Okay, coming to the end, it will be the platform centric data science in the future. I'm sure, as I said, within 5 years, it will be the most platform centric data science as an integrated platform. Why? Why, in the sense, it reduces the architectural complexity. We don't want to rely on the isolation tools like separation of system what we use. So it reduces the architecture, and we get more generation of insights what we need to make the decision. And it is the scalable operation for both governance and managing roles in the security options. And it increase the impact of the organizations what they expect from the end users. So it will be useful in the future platform centric data science. That's it. Thank you for your attention, and I hope it is a short brief and it is so useful for you all. Thank you. Thank you, sir.
any app for garbage system. So that's the result is canvas 3 apps. So the first app doesn't have it. All the 3 apps are not having any live system.
So since your application is also lagging in many things, see, it was just only intimating whether the vehicle is here or not, whether when it will come, just for intimation. See, from the place where the garbage needs to be collected, then it needs to be dispersed. That's a long way process. You are creating only for an user. Then for what if a government is buying your project, what is the use for the government?
Ma'am, there is no scheduled systems in the government. For example, I'm from Thuthukudi, and in our street, the garbage vehicle, if today it is coming in morning means some the random days will not come, right? So our resident peoples will pick up the garbages from their home and they will put it in the street corner. So it will make the street ugly. So if it is followed by the government, the cities will be more cleaner and the people also will do the process.
So as a user, it is very, very good. But when it comes to government, how it is will be useful?
For government, that only, ma'am. If today the garbage vehicle is not coming, as I said, the residents will take their garbage bag and put it in the street corners. Because they have to clean their house. They didn't care about the streets, right? So if this is followed by the government, the street will be cleaner. The government will get profit only.
Thank you. Such a wonderful presentation. அவன் சொல்லிட்டான்ல எக்ஸிஸ்டிங் இருக்கு. ஆல்ரெடி சென்னை மாதிரி மெட்ரோபாலிட்டன் சிட்டிஸ் இது ஆல்ரெடி இம்ப்ளிமெண்டட்.
இம்ப்ளிமெண்டட்னா ஷெட்யூல்ஸ் வந்துட்டு நம்ம ப்ராப்பராக லைக்
இல்லை நீங்கள் சென்னை எடுக்க வேண்டாம், மும்பை பெங்களூர்.
Thank you, team, for your wonderful presentation. Next, I would like to call upon Ashwini, Mani Saravanan, Sri Pranava Ganesh, Vignesh, Madhumita from Kamaraj College to present their presentation on the topic Sentimental Analysis and Visualization of YouTube Comments using NLP. Please come onto the stage. அந்த போடியம் மைக்கில் பேசணும் பேசலாம். மூவ்மெண்ட் வேணும் அப்படின்னா இந்த மைக்கை ஜஸ்ட் ஆன் பண்ணிக்கோங்க மேலே. ஆக்சுவலாக லைவ் ஓடிட்டு இருக்குது, அதனால தான். இது ஒன்று அப்போ நீங்கள் கொஞ்சம் சதமாக பேசுவீங்க, இதில் மட்டும் பேசணும். ஆனால் யார் பேசுகிறாங்களோ அவங்க கையில் இது இருக்கட்டும். ஓகே.
கவர்மெண்ட்டோட வெப்சைட்டோட போஸ்ட் பண்ணுவோம். குட் ப்ரெசன்டேஷன். ஐயோ இவங்க யார் நம்பர் இல்லான்னு பார்க்கலையே, நோட் பண்ணி பார்த்துட்டீங்களா? எழுதிட்டே வரீங்களா நீங்கள்? லஞ்ச் வந்துடுச்சா? அப்புறம் அப்படி இப்போ நடந்துட்டு இருக்குமா? அப்படி இருந்தால் நல்லா இருக்காது. அப்படி நடந்தாதான் சென்டிமெண்டல் அசஸ்மெண்ட் பார்க்க மாட்டோமா? அப்போ நீங்கள் பார்ப்பீங்க போகிறீங்க சட்டுவோம்.
Good afternoon, Good afternoon, everyone.
Please respond.
It's my pleasure to introduce ourselves. And I am Ashwini. He's Pranav. He's Mani Saravanan. She is Madhumita. And he is Vignesh. And I'm like to ask a question about our topic. How many of you are using YouTube nowadays frequently? Then how many of you have an own channel, YouTube channel?
Make it little louder. Make it little louder.
Now let's dive into the technical background of our project. Imagine you want to analyze the sentiment of YouTube comments and display the results on a website. That's exactly what our project is all about. At the core, we are using BERT, which is a powerful NLP model developed by Google in 2019. The reason behind choosing BERT over other models is because BERT is already pre-trained on massive data sets like Wikipedia, and also BERT reads context from bidirectionally, which means it reads the context from left to right and right to left, which ensures to predict the.
Move on to the results. Move on to the results, and your proposal. What is the methodology used? Okay. Is it multimodal? Could you show me that your proposal? Could you show your proposal? Could you highlight your proposal? நீங்க என்ன methodology follow பண்ணீங்க? Okay, fine. Let me see the results, the accuracy of your approach. Okay.
From there, I will identify whether it is a good content or a bad content, and then I will give the recommended session. Like if I have a YouTube channel, I gave the if I have the YouTube channel, I gave the URL of my first content, and it will show how many positive, negative, neutral comments. From that, I will tell that person if you give the content like this, you may reach so much like that.
Okay. Why did you choose BERT? Why not GPT 4.2? Why not other models?
Because BERT analyzes the sentiment analysis. It gives accurate terms. So we choose BERT.
Okay, then what is the accuracy of BERT and what is the accuracy of GPT models, which you have compared?
Actually, we compared Radar and BERT. We didn't analyze the GPT.
Okay, what was the results or performance of BERT?
Radar, not that much. If the in the Radar there is so lag. If the NLP model is some persons reads the BERT model reads bidirectionally, but the Radar models didn't read, and the accuracy differ from each other. So we choose BERT.
Great. Shall we appreciate them? Good. So the next team from on the mic. Cardless mic. So the next team to present from Kamaraj College. Next team from the college. Whoever is ready, please come forward. So you'll be given only 10 minutes. You'll be given the maximum of 10 minutes, maximum. Okay? You'll have to complete your session with the next. Your talk with them. Good. Do you want this? சாப்பாடு நிப்பாட்டல பேரல் கிடையாது இப்போ சொல்லிட்டு ஆன்லைனில் ஒரு copy of this book for your. Yes, you can start. So audience there, please wait for a while. We are going to break for lunch. So delicious lunch is arranged. We'll just listen to them first and then we'll move on.
Good afternoon, everyone. Good afternoon, everyone. We are going to present our project on detection of skin disease. First, I would like to introduce our team members. Myself, Ashna Devi. She is Anupriya, Pradeepa, Madhumita, Pradeepa. Introduction. Skin diseases are common health problems and overall the world. So, yearly detection of skin disease is very important because it helps to prevent from serious situations, and in many areas there are dermatologists are not available, so the people may not get the right diagnosis at the right time. Based on that problem, we have used AI to detect this skin disease using image visualization.
And problem statement is skin disease is the most common health problem worldwide, as many people were affected through that. Many skin diseases have the similar symptoms like itching, rashes and redness. So these are the common rashes. When it's come to diagnosis, many diseases have the similar conditions. So while we are going to the doctors mandatory is visual examination. So that may be misdiagnosis also. So we used Python and AI for that, and methodology will be carried on by Anu.
So now I will explain the methodology of our system. So first, the user uploads a skin image through the app, and this image becomes the input for our system. So next, the image goes through the processing step. So where it is resized into 224 into 224 pixels. So this standard helps the CNN model to process the image efficiently. Then after resizing, we normalize the pixel values. So next, then the image is passed to the CNN. So the CNN automatically extracts the important features such as skin color, variations and patterns. So based on these extracted features, the trained model predicts the possible skin disease. So finally, the system displays the predicted disease along with the accuracy percentage, so which indicates the confidence level of the model's prediction. So now I am going to tell about technology. First tool we are using TensorFlow, which is which is give the accurate and less value for this. And OpenCV is used for the it's used to run the code, and MobileNet is used for detect the accuracy and detect the name. Streamlit is used for the offline course. It will run in also in offline. Then we made a prototype for this. By using Python language, we made this. On the we collected data set, and in data set there are many skin diseases images are there. We trained the model by checking it. The image was given by the user is similar to the data set, is correct or not. Then it will use by the TensorFlow. It will run the file one by one to check whether it is similar or not. Then this is the Streamlit, which is run in offline. When we give some image like skin disease, it will give the name, give the disease of the name, and then it will give the accuracy of it.
Now we going to the conclusion part. First is in the project we are developing a AI based skin disease detection. It is used to analyze image and related to identify the disease. The second is the system accuracy. We are used the deep learning for the accuracy, and the third point is it is advantage of the system. It can work in offline also. It is useful for rural and poor network condition. And last point is the system is not replace the doctors, but it is help for doctors. Thank you.
So it is also a very wonderful presentation. You have worked on skin disease detection, right? And why? This is my primary question, and I ask in this question in my own clarity. Why did you choose this particular topic, or why did you name this work so? The work in the title.
சார் அந்த டிசீஸ் கண்டுபிடிக்கிறதுக்கு நிறைய டிசீஸ் வந்துச்சுன்னா அந்த இது கண்டுபிடிக்கிறதுக்கு அவங்க அதை அலட்சியமாக எடுத்துப்பாங்க, டாக்டர்ஸ்கிட்ட போக மாட்டாங்க, அது ஈஸியாக அவங்க ஃபைன் பண்ணுறாங்க.
Okay, so I'll make it more clearly. You have worked on CNN, you have worked on CV, and NLP is also included, am I right? Okay, but somewhere you have mentioned NLP, then it might be wrong. Okay, so having worked on all these areas, and you have chosen MobileNet as one of your CNN models, and having all these things, why did you choose this particular topic? Why not some other topics, like using CNN, using CV, or open CV? Why did you go for this topic?
நார்மல் ரெமடிஸ்னாலே யூஸ் பண்ணிகிட்டே இருந்திருக்காங்க. ஃபுல்லாகவே அது ஓகே, இது வந்துட்டு போயிட்டே இருக்குது, ரெமடிஸே யூஸ் பண்ணிகிட்டே இருந்திருக்காங்க. அட் த லாஸ்ட் அது என்ன ஆயிடுச்சு, அது ஒரு சிஸ்ட் மாதிரி ஃபார்ம் ஆயிடுச்சு. ஸோ they didn't even know what is an acne and what is the exact thing what they got. So we want everyone to know that gain the knowledge about what is the thing they got. அப்படிங்கிறது தான் எங்களோட மோட்டிவ். அதனால தான் நாங்கள் டிடெக்ஷன் ஆஃப் ஸ்கின் டிசீஸ் சொல்லுவோம்.
So now it's kind of good.
great.
Only one question. What type of input? What is the input data? Image data. So which type of image you have taken?
Like JPG, PNG.
JPG in according to medical, what type of data? MRI image or which image?
It's not normal skin.
Normal skin image. So what are the features you have taken? Image and colors.
Textures.
Good.
Good. We'll appreciate their work. They are online. Let them So we are breaking for lunch. If at all somebody want to present, you can stay back and present, or else we can go for lunch. So, yeah. And one instruction is those who are staying in hostels, please see that you are taking your bags here. Yeah. Lunch முடிச்சிட்டு கொஞ்சம் ரிலாக்ஸாக போய் பேக்லாம் திங்ஸ்லாம் எடுத்துகிட்டு வந்துருங்க. Hand over the keys to the representatives. Girls, hand over your keys to Ms.